Okay, guys, last lesson of the year. Holy cow, this is kind of crazy. All right, so we're going to look at the graphs of logarithms today. And I think it's really important to consider the graph of logarithms by starting with the graph of exponentials. Because remember, your exponential functions are inverses of logarithm functions. So if I plug in -1 in for 2 to the x, that's 2 to the -1 or 1/2. Plug in 0, 2 to the 0 is 1. Plug in 1, 2 to the first is 2. Okay, so we've not had a ton of time to really emphasize this, but all exponential functions have a horizontal asymptote on the x-axis. All right, -1/2. I'm going to graph these 3 points, 0, 1, and 1, 2. All exponential functions get big really quick after, and this is getting closer and closer to the x-axis, but it never crosses it. This is what all exponential functions look like. Let's think about what does the inverse look like. Inverse graphs always reflect over, let me get a hold of this just a second, over the y equals x. That'll be important, and hopefully we'll be together a whole lot more next year, and we can talk about this more in detail. But inverses always, it's almost like whatever the graph looks like, you take this corner, fold it over to this corner, and however this graph maps onto the other side is what the inverse graph looks like. Let's consider, whenever I talk about inverse graphs, the x's and y's switch from the original. So this becomes 1/2, this becomes -1, this becomes 1, this becomes 0. All of the x's turn into the y's, and all the y's turn into the x's. So let's think about and if everything just flips for exponential function, there is a horizontal asymptote at y equals 0. If we're switching the x and the y, doesn't it make sense the inverse would have a vertical asymptote along the y-axis? So it flips this way. Now, with me using the slate, this is not super accurate, so kind of use your imagination. But if I were to take this corner and flip it over to this corner diagonally, hopefully you can kind of see how this maps onto the blue. Okay. Now, if you consider this blue line, I want you to think about what's the domain of the blue line. Notice it's never going to touch the y-axis. That means x is never going to be 0. You never will cross into where x is negative. The domain for logarithms, x has to be greater than 0. That's what they're saying down here. And the range, how far down does the graph go? All the way down, and it goes all the way up. You could say all real numbers for the range. We could also say -infinity to infinity. Either one of these answers is acceptable. Hopefully your R's look a little better than mine, but all right. So this is when you've got an exponential growth function that flips. So this would be log base 2 of x. Let's consider 1/2 to the x. All right, so if I plug -1 in, -1 or 1/2 to the -1 is 2. Anything to the 0 power is 1, and 1/2 to the first is 1/2. So think about how 1/2 to the x is the same thing as 2 to the -x. What that does with this pink graph is it flips everything over the y-axis. So let's think about that. -1, 2, 0, 1. So it looks like this. That's your exponential decay with an asymptote along the x-axis. And let's consider if we flip this. This is a little bit trickier to see, I think. If I flip this one over, this goes up here. Kind of like this. This is kind of goofy, but so this would be a log to the 1/2 base 1/2 graph. This one's a little trickier, but this one I'm not so worried about. This one you need to understand your log of base whole numbers will always have that general shape crossing at 1, 0. This will be important. Remember in the last section we talked about what's log of 1, whether it's ln, log base 10, log base 2, whatever it might be, the y is always 0, and we can see that right here. That corresponds to anything to the 0 power is always 1. So the inverse log of 1 is always 0. Okay, so this kind of gives us our domain and range for both exponential and logarithmic. Notice what happens with the domain and range. With domain of exponential, x is all real numbers. We can plug any number we want in for x and not have any problems. But our y will always be greater than 0. What happens with inverses? Our x's and y's switch. So where the range has to be positive and the domain is all real numbers, they switch with its inverse. Now the domain has to be positive and the range is all real numbers. Where the asymptote for your exponential is horizontal, all general, y equals 0 unless it's moved up or down. And all logarithmic starts out with x equals 0, a vertical asymptote, unless it's shifted. All right, so let's consider this example. There's a whole lot to this example, so just kind of bear with me. But the last example of the year. Okay, so first of all, x minus 1 is what as a transformation? What will this do to the graph? If it's with the x, it shifts it the x direction, and it's always the opposite. So it's going to go to the right 1. Plus 1 is moving it the y direction. So when we talk about moving it left, right, up, and down, it looks like a vector. The top number tells us the x direction. It's going a positive 1 to the right 1, positive 1 up to the y. So it's up 1 to the right 1, up 1. Okay. So this is just saying what's the basic transformation to the basic graph. All right. Domain and range. In general, x has to be greater than 0. So what will this do? That means that x minus 1 has to be greater than 0, or x has to be greater than 1. That's our domain. Our range for logarithms is always all real numbers or negative infinity to infinity. Any type of asymptotes and axes intercepts. Logarithms always have vertical asymptotes. It's always what makes this equal 0. So it's the vertical asymptote. What makes x minus 1? Oh, my slate is not working. What makes x minus 1 equal 0? When x equals 1. I'm going to move this part over. Okay, the axes intercepts If I plug 0 in for x, that would force me to take log of a negative. So there is no y-intercept because x cannot be 0. Okay. So what happens if I plug 0 in for y? This allows me to find the x-intercept. So I need to subtract 1. Now we can do this a couple of ways. We can rewrite exponentially. I'm just going to raise both sides to the power of 2. So that cancels this out. 2 to the 1/2, or 2 to the negative 1 is 1/2 equals x minus 1. Add 1. So 1 and 1/2, or 3/2, is our x-intercept. All right, so sketch the graph. That's a bad graph. All right, so the first thing I want to incorporate is my vertical asymptote is at 1. Hang on. Okay. We can put our x-intercept at 3/2, 1.5. Then let's just pick some values. All right. What happens if we plug in 2, see that next one over, for x? If I plug 2 in for x, I get log base 2. 2 minus 1 is 1. What's log of 1? Always 0. Plus 1 is 1. So that gives me a coordinate point of 2, 1. Now, when you're working with logarithms, first of all, we can kind of see how this is going to go straight down here. Another value, if we're doing base 2, what number could I plug in here that I can find a value to? If I plug in 5, what that gives me is log base 2 of 4 plus 1. Well, log base 2 of 4, that's log base 2 of 2 squared. So this cancels, and 2 plus 1 is 3. Let's see, 1, 2, 3, 4, 5. 1, 2, 3. So it kind of just gives me a general shape. So notice we kind of just found a couple of coordinate points to find that shape. I know with this asymptote, as soon as it crosses, it's going to get really close. I just was finding a little bit of a shape here. It's not the best graph, but kind of use your imagination. Okay, the last thing we need to do is find the inverse function. To find inverse functions, that's where we want to switch x and y and solve for y. Let me see if I can fit it in down here. So we'll have x equals log base 2 of y minus 1 plus 1. In order to get to y, I need to first of all move the 1 over. So minus 1, x minus 1, and this is all connected, equals log base 2 of y minus 1. Then I'm going to either rewrite exponentially or raise both sides to the power of 2. So that cancels out my log base 2. So I get 2 to the x minus 1 equals y minus 1. To get y by itself, I just add 1. 2 to the x minus 1 plus 1 equals y. And it's always important. This is not what the y equals in the original. We're looking for the inverse function. So I'm going to restate this y as f inverse equals 2 to the x minus 1 plus 1. And that's it.